I'm Amir, a software architect at ARMO. I'm also a core maintainer of Kubescape, a CNCF incubating project, and a GopherCon speaker. This is my first KubeCon as a speaker. You can find me on LinkedIn or GitHub. So the agenda for today is we're going to start by looking on the differences between CRDs and aggregated API servers. We'll see how these aggregated API servers work, and we'll take a look on a use case, how we in Kubescape develop our own server. And also, we'll go over the lessons we learned in production and like when to choose this path and when not to. So that's about like the agenda for today. And before I dive in to talk about aggregated API servers, let me set the context on Kubescape. So Kubescape is a security platform. It aims to cover all aspects of security aspects in a single project. So what we do is we do vulnerability scanning for container images. We do configuration scanning of workloads against best practices. We also do workload behavior monitoring with eBPF. And so in general, we generate a lot of data. So if I look on the vulnerability scanning flow, so in order to be able to create a vulnerability report, first you have to generate an SBOM. And so what we do is that we generate an SBOM. An SBOM is a list of all the components that make up a container image, and it can be quite large. So once you've generated an SBOM, it passes through the vulnerability scanner, and then it gets sent to some external API. This is how we used to work like back at the beginning of Kubescape. And so becoming open source had its requirements or challenges. So in order to become like a fully open source solution, we looked in a way that we are going to keep all the data inside the cluster. And one of the important things for us was that our users were Kubernetes users. So we wanted them to not learn like a new API, and so that everything remains in the Kubernetes ecosystem. And so Kubernetes basically gives you two ways to extend its API. One is with CRDs. CRDs, or custom resources, are very easy to implement. It's like the lightweight route. You define a new resource type in a YAML. And basically, the Kubernetes API server does all the heavy lifting for you. So you have RBAC out of the box, validation. You can use CL expressions for like complex validations. And everything gets stored in etcd. And so the second option is with extension API server. That's the main subject for the talk for today. So like with extension API server, you build your own standalone API server, like Kubernetes does. And so you're fully in control when it comes to storage, discovery, and all the logic and behavior of that server. There is a steep learning curve, I can assure you. That this is what we'll learn with Kubescape, and you'll see in a minute. You'll learn more about it in a minute. And so it also comes with high operational cost and maintenance. So these two options like have very different trade-offs, both in terms of complexity, control, and operational cost. And so, as I said, CRDs are very simple to implement. That's an example of a CRD. So you define the scope, whether it's a namespace or not, the name, group, and you provide a schema for validation. Now, raise your hand if you've ever seen this error. Nice. So this error means that you've hit the etcd 1.5 megabyte limit. Here it says 3 megabytes, but That's because the request allows you to send, that's the overhead of the request when it eventually it gets stored in protobuf, which etcd has a 1.5 megabyte. So I really hope that you didn't thought about increasing these limits because that's not a good practice. So this is where the journey begins. So since we were generating large objects, we knew we had to develop our own API server. And a good starting point for that would be to either the sample API server that Kubernetes gives you or the API server builder. So we started with forking this project. It gives you code generation, all the wiring done out of the box. But from that moment, you're on your own. So the first step in order to replace etcd was to implement the storage interface. And for that, we also had to disable the watch API. And to understand better what API aggregation means in Kubernetes, let's look at the Kube API server code that's taken from the upstream. So we can see it's built in a chain. So first, you have the built-in types, and then you have the CRDs, and lastly, you have the aggregated API servers. So each part of the chain tried to handle the request. So for built-in types, and then for CRDs, and eventually all the resources that are handled in your own server. So this architecture is quite flexible, as you can see. You don't have to write new code for this. So for a CRD, how the request flow looks like. So the client sends a request to the Kube API server. The Kube API server takes this request and stores it, writes it locally, the resource that you're creating, to etcd. So everything is safe, constrained, I would say, but it's limited to etcd. With an aggregated API server, so you've sent a request to the Kube API server, and that moment, the Kube API server understands that it needs to route the traffic to an external API. So from that moment, the API server can do anything with the request. And that comes with a risk. So we'll see in a minute what risks are involved with this flow, but it really can impact the entire cluster if you're doing something very bad. So how's the routing work? So we have these API service objects, which basically tells the Kube API server for group X and this version, forward the request to this service in the cluster. Authentication is also part of this resource. So you can either provide the CA bundle, or you can skip TLS. That's up to you. And so if we want to visualize how it looks like, so the Kube API server does the discovery for these API service objects. And these API service objects each has its own definition. So you can have multiple API services for multiple API groups and for different versions of the same API group. And so authorization is done at two ends. In the incoming request to the Kube API server, and also in the, your external API server. These RBAC checks are important because basically the client can communicate directly with the external API server, so this is why it's needed. And if you've done everything correctly, so if you type kubectl get API service, you should see your definitions and the available should be on a true. And so once discovery is done, you should be able to see your new resource kinds with the kubectl API resources standard command. So when you're developing your own API server, this is something that I think someone should get familiar with. So there is this thing called strategy. Each type has a strategy. You have them for built-in types. You can look at the code in the Kubernetes on GitHub. And so it's kind of hooks that the request goes through before it gets written to the storage. And in these hooks, you can define your own logic, basically. And so let's look at some of the, I don't know, interesting ones, I would say. So we have the prepare for create, which is for resource creation. You get the object, you cast it, and from there you can put some creation logic. We have the prepare for update. You receive the old resource and the new resource, and put some custom logic based on that. And so in Kubescape, for example, we really used it. So what we are doing is we looked for a way, for example, to resource update based on annotations. So we need to add a reference of the old resource and the new resource, and then decide if we reject or accept the request. So that's real cool. And we have the validate function, which basically does static validations on the values in the resource. So you remember these huge SBOMs I talked about? So we had to get creative. And so when we developed our API server, we splitted the actual resource on the disk to two files. One contained only the metadata, and the other one contained the full object. And when you are listing resources from the API server, you will get only the metadata files. And that is really important in terms of memory, CPU, and you can understand why. So this is how it would look like. So the spec was null. And in order to get the full resource, you had to specifically ask for it using a get. And so this was like, I don't know how to say it. Like, we thought that we did like super optimization and we solved all the issues, but then we were going to production, and that was challenging. So that's the memory usage of our storage pod. And if I zoom in, you can see it's like 93 gigabytes of memory. So we knew we had to change a few things. And it wasn't like one shot. It was a journey. So the first step we took is we migrated to gRPC and protobuf for the client-server communication. It wasn't very easy, I would say, but eventually we managed to do it, and it yielded in a significant improvement in both memory, CPU, network, both for the client and the server. As for the second step was change from JSON encoding to GOB. So GOB is Go specific, is a binary format. So it was a major change. It optimized storage by up to 60%. And one more step that we took was to work with direct I/O, as it reduced the container memory footprint, because direct I/O bypasses the file system cache. And so the third step is that we didn't really support pagination. And as you can imagine, listing thousands of resources in a single request was not a good idea. So we knew that this is something like a tech that we need to solve. And so how we solved it was within SQLite DB. So what we were doing is that we were saving the metadata in SQLite DB and using the row ID when someone sends a get list request to get the next page. So let me be very clear about the risks. So you can impact the entire cluster if you're doing silly stuff, and it's very easy to do that. So since you're running like critical infrastructure, your extension API server must respond quickly, and like things like server crashes can prevent operations from happening, like namespace deletion. You might get flooded with requests from the Kube API server. And so this is why to overcome these, you need to be aware of the risks and put some good alerting, monitoring, and make sure that your pod is highly available. So I have a few takeaways I want you to take from this talk. Start with CRDs. They're easy to implement. I think they should be like your default choice. Kubernetes does all the heavy lifting for you. But extension API servers are for when CRDs can't do the job. So if you need custom storage, you'll have data size limitation at CD. You want a different backend. That's the point where you can start exploring these options. And so if you have decided to build one, so keep in mind that you're now running critical infrastructure and that you're ready for all the operational burden, because we've learned it the hard way in Kubescape. Thank you very much. I'm here for questions. I think the AV guy there. Yep.
Okay. So you mentioned earlier in the presentation, fairly early on, that when you switched from SED to a different backend, that you had to no longer support watch as a thing. As far as I'm aware, that makes it so that it's no longer Kubernetes conformant for your API server. How do you handle maybe somebody wanting to perform like controller-based operations against your APIs? Like what's the directive that you have to give end users that maybe want to react to changes or something like that?
Okay, so for our usage, we didn't need the watch. And so you need to implement a watch. That's when you take the interface, you must implement the watch. So we're like just doing equals null. Okay, so it works, yeah, but like it really depends on the use case. I mean, Ben, like maybe you have. Maybe I'll bring you a mic.
Can you turn on the mic, sorry? Mic? So, hello? Not working? Okay.
Yeah.
So, we did return the support for watches because we did use at some stages the watch, but it's like a super mean problem for us because the objects are really complex and really big. And you can have Kubernetes objects which are not supporting watches. It's okay to answer like no for watches. Yeah, but again, think about it. Like think about the use case. It's an SBOM. So does it make sense to like watch for SBOMs in general? So it's not a configuration object. It's not a status object. It's I know it's something like you know, partially compliant, but there are like existing examples for other projects not supporting watches. So it's kind of, working.
Okay, thank you.
Yeah, we did a lot of mistakes, like for first timers. Yeah, go ahead.
Hi. In the beginning, you mentioned that one of your main driving factors was you didn't want to introduce a new API for your client, so you wanted to use the Kubernetes API.
Right.
Given all of the challenges that you described, was that goal, achieving that goal, was it worth it with all of the effort that has to go into this?
That's an open question. We're still trying to answer.
And follow-up, would you recommend somebody in a similar situation go down this path or go the old school way of just create an API in an HTTP server and store stuff in a database?
Yes, so I'd say think twice. That's like what I would say, because there is a lot of high maintenance cost, both for developers and for DevOps taking this. And so, yeah, it's not a plug and play, that's for sure.
Thank you.
Hi. Thank you for the talk. Super interesting. You mentioned that the sample API server didn't support gRPC out of the box, and you had to add that. Did you contribute that back upstream?
There was no need for, if I remember correctly, there's another developer that dealt with this challenge. I think it was just about forcing it to use gRPC. It's not that big of a code. It's for the communication with the HTTP headers, if I remember correctly. So, but I can share the code with you or with anyone who is interested.
Great.
Yeah.
Great. Thank you.
Sure. By the way, we're available on the Kubescape channel in CNCF, so feel free also there to raise any questions that you might have.
Thank you.
Sure. Oh. Thank you.